Now I am wait. So I will wait. Now I'm waiting for you to join the YouTube channel. Okay. Okay. So the number of people joining Zoom is 29, but still some of you haven't joined YouTube because the Zoom camera is not on the board. Thank you, Lu. Thank you, Luwe. You sent us the link. Thank you. Okay, now we are there. So today we want to continue the lesson. As you have seen, the topic would be the application of the chain rule according to the book. So this would be the lesson on page 85. But before doing that, I just promise you to go through a little bit about how we prove the chain rule. The real proof for the chain rule is a little bit technical, but I want to go through what is given on page 82 in the book, Origo Matematik 4, yes? So I want to more or less review those lines, but you will see what are the technical difficulties in proving the chain rule, okay? So if you remember, we had this for the chain rule, that if I have a function h of x, which is f of g of x, then we learn that its derivative, we actually you trusted me on this, but now we want to show that this is more or less the case. So the derivative of h is equal to f prime of g of x multiplied by g prime of x. So that was the chain rule we were talking and using so far. Okay, but now I want to prove this one. So do you remember what was the definition of the derivative? So let me just write and clean it. The definition of the derivative of any function f, don't get confused with this f and that f for the time being. This is the generic definition of the derivative. So it was f of x plus h minus f of x divided by h when h goes to 0, yes? That was the generic formula for the definition of the derivative. And then you see that we use the letter h here to denote this increment in the x direction. And then I am also using the letter h here. So if you don't mind, let me keep the letter h as before, because we get used to this, we have got used to this. But let me change the name of this function so that there is no matter of confusion between this h and that h. Here h is the increment in the x direction, and here h was the name of my function. So I will change the name of the function because I don't want you to get confused between these two same symbols, okay? So, for example, let me change the letter h to, for example, s. Okay, and then we want to show that S prime of x is equal to that. Okay, so I want to start proving the derivative of S. So what is my starting point? There is nothing I can do except using the definition. So I will write S prime of x is the limit of S x plus h minus S x divided by h goes to 0. Yes, so that is the definition of the derivative of the function S. It's just the normal definition. But now my function S is defined in terms of f and g in this composed way. So what should I do? If I want to continue, I have the limit part, h goes to 0. I have this fraction line, h. I have the negative sign here. S of x is equal to f of g of x. So it becomes f of g of x. And then I want to write something for S of x plus h. Can some of you help me to write that so that we can also test that everything is working fine? Can you say what should I write instead of S of x plus h now?
F of g of x plus h.
Yes, so let me increase the volume so that I can hear you well, but that was correct. Oops. This is already 100%. Okay, so I cannot increase my volume more than that. But I heard you. Yes, that's correct. So what we do, we just replace this x with the new input. Yes, so this becomes f of g of x plus h. So let me write it more properly here now. Minus f of g of x. That is my definition. This is what the definition of derivative brings me. Yes? Okay, the technical thing here is this. I write this as the limit. You need to be patient, so let me write it down and then I will explain to see why this is the case. Okay. Instead of dividing it by h, I divide this expression by g of x plus h minus g of x. But I have to compensate for this change, yes? So because the denominator was h, I am writing it in this form. So if I want to compensate for that, I would multiply it by this expression. Yes, hopefully understandable. And of course, there is already a flaw there, which I don't think the book is addressing it. No, I don't think they are actually addressing. So that is the important point. That's the only flaw in the proof that we have. H goes to 0 because if they want to talk about that, that's a little bit technical. So this is why they avoid it. But the good point is that that is actually a very good sketch of the real technical proof. So we divide by this and multiply by that. Let us check that. Is this equality again the case? G of x plus h minus g of x. And this g of x plus h minus g of x are cancelled. And then what is left for me is again one single h in the denominator so that I can write it again. So I hope that you understand that there is no difference so far, except one technicalities. I will come back and talk about that a little bit later. So what I want you to understand is that this a little bit complicated expression is exactly equal to the previous expression, because this gx plus h minus gx and this one will cancel out, and what is left from the numerator is the same expression, and what will be left in the denominator is the same h. Yes? Okay. Now there is a theorem in limits. We haven't talked that formula. So by the way, let me put a pair of brackets around this. Let me put, the whole expression, I want to take the limits. But this is a product of two functions. There is a theorem in limits that if the limits of functions exist, then the limit of the product of those functions also exists, and it is equal to the product of the limits. Okay, so in principle, I can write it as the limit of the first function, f of g of x plus h minus f of g of x divided by g of x plus h minus g of x. H goes to 0, multiplied by the limit of the second function, which is g of x plus h minus g of x. H goes to 0. Okay? So this is the product of two functions. I want to calculate the limit of the product. If the limits of each individual function exists, then I can write it as the limit of the first part multiplied by the limit of the second part. And the reason that these limits exist, because if you go back and see how I stated the chain rule, I told you that g is differentiable at x, f is differentiable at gx. So this is the conditions that we have, and then we want to use those conditions. Okay, but hopefully this is familiar for you. Yes? Can you tell me what can I write here? Instead of this limit, what can I write? Anyone?
G prime of x.
Yeah, that's g prime of x, exactly. That is the famous definition of the derivative. The only difference is that instead of using f as my function, I have g as my function. So this is nothing except g prime of x. And that is very good, because if you go back and look to the formula in the chain rule that we want to prove, you see that you have multiplied by g prime of x, and that is the g prime of x coming from, where the g prime of x is coming from. So far, so good. But the problem is that I need to understand this bit. So let me give this a name L, and I want to start calculating L. Okay? This is not exactly in the form of a derivative, but for calculating L, I introduce a new variable. So I will say that let k be defined, this semicolons equal means defined to be equal, g of x plus h minus g of x. Okay. Now what happens if I want to see that this is a new variable, I want to see what happens for k when h goes to 0. Okay, when h goes, so we know that g is differentiable at x. Therefore, there is a theorem. I talked a little bit about that in one of the previous sessions, but I told that these are more advanced mathematics. We don't want to delve into it. But g is differentiable at a point x. Therefore, g is continuous at x. Okay? When g becomes continuous, so this means that the limit of g of x, and so let me write hence, the limit of g of x plus h when h goes to 0 becomes exactly equal to g of x. That is the meaning of g being continuous at x. And then this means that the limit of this difference is actually equal to 0. If the limit of this one is equal to the limit of that one, it means that the limit of the difference is equal to 0. But this is nothing except my k. Okay, so this means that the limit of k when h goes to 0 is equal to 0 when k is that guy. So simply speaking, it means that when h goes to 0, k goes to 0. Simple as that. So when h goes to 0, this implies that k also goes to 0 by this definition that I have made here. Okay? So remember that I am calculating s prime of x here, because I have to erase here. But you need to remember that I am calculating s prime of x. Okay, now let us go back to my limit, L. So my question mark was, what is L? So if I want to answer this question, instead of h goes to 0, I realize that h goes to 0 implies that k goes to 0. So this can be written as the limit. I want to write everything in terms of k instead of h. K goes to 0. Okay, what can I write for the denominator? For the denominator, I can just simply write k. Yes? So this becomes k. But what can I write for the numerator? This one is not touched because it doesn't depend on my variable h. Yes? Here, h is the variable of the limit. X is considered to be a constant. What I am varying, I am sending h to 0. So it means that h is gradually shrinking, getting smaller and smaller, but x is fixed. So this part will not be affected by this change of variable. So this becomes minus f of g of x. But what can I write here? This depends on my variable h. But that is also very simple. You just move g of x from the right-hand side, from the right-hand side to the left-hand side. So this implies that g of x plus h is equal to g of x plus k. So this means that instead of g of x plus h, I can simply write g of x plus k. Yes? So this becomes f of g of x plus k. Yes? Now, I don't know, I want to wait a little bit for you to test your understanding. Can you write something for this? Is this limit familiar now? Let me write something here for you in the box to help you a little bit. So if I ask you what is f prime of x, what is your answer? You say that this is the limit of f of x plus h minus f of x over h. H goes to 0. This is the normal definition. But is there any difference between saying h goes to 0? Question? Do you have any questions? Okay. Yeah, I will ask you again. If h goes to 0, I write h, but it doesn't matter if I change the name of h everywhere to something like k, because h is something that I use to show what I am doing with h. I am sending h to 0. It doesn't matter if I have another letter, but of course I cannot use letter x here because x is already reserved for this. Any letter except x I can use. So let me write it with k instead of h. Okay? Now, compare this one with that one. You immediately realize something is playing the role of this x if you compare this limit with that limit. Yes, Alex, if you wanted to answer, you can answer now if you want to.
Yeah, that the g of x is playing the role of x.
Yes. So the answer to this limit is f prime of x. It becomes what?
The f prime of g at x.
Exactly. So this becomes f prime of g at x. Okay? So, and that is exactly this part. So you see, this limit L is the derivative of f at g of x. This limit is the derivative of g, and they have been being multiplied here. So this means that if I multiply L by g prime of x, it means that I am multiplying f prime of g of x by g prime of x. This becomes the derivative of my function s. Yes? So this is actually, you see that it is technical, and there are many things involved. One thing I actually addressed you, but you are not at that level to understand these things in a very rigorous way. So, but you need to remember, I told you that the points at that the function is not differentiable at. Yes, we talked about these kind of things a little bit before. There we learned that if g is differentiable at a point, g is continuous at that point, and then this is necessary to conclude that k goes to 0, which was essential for my reasoning because I need k goes to 0. This is one thing. Another thing that I didn't address is that you see I divided this expression by this and I multiplied it by that expression. That is quite okay, only under one condition. And the condition is that this should be guaranteed not to be equal to 0. Okay? And this guarantee, we don't have it. For example, there is a very simple function that you can imagine in your head for which g of x plus h minus g of x is 0, no matter how I make h small. Can you guess of any function, for example, so that g of x plus... Yes, exactly, very good. Any constant function has this property that g of x plus h is the same number that g of x, and when you subtract them, it becomes 0. You might say, so this means that this proof is at least not valid if my g function is a constant function. But you might say that this is not an obstacle anymore, because if g is a constant function, then the derivative is 0, and then because g is a function, is a constant, f of a constant is also a constant, and the derivative of a constant is again 0. So this means that the left-hand side is 0, the right-hand side is 0. So you might say that this is not an obstacle, because if the function is a constant, the chain rule is automatically satisfied, not because of this complicated calculation, but because the right-hand side is 0, the left-hand side is also 0, that's completely okay. So this means that I would say that if g is not a constant, this is the proof. If g is the constant, I don't need the proof at all. The proof is much simpler. I just compare the left-hand side and the right-hand side. Both of them become 0, and then that's okay. But the problem is a little bit more serious than that. The problem is that, how do you know that the constant functions are only functions of this property? Yes, might be there are some other functions that this can be 0 no matter how I make h small. Okay, so for example, if I have some number, some zeros for my function, I can make h a little bit smaller to exclude those points, and then I will be on the safe side for this division. But how do you know that this is always possible? And it turns out that no, it is not sometimes possible. Even in those cases, the chain rule still works. So this is a flaw. So I mean that this is not a flaw, but this is not a complete proof. This is a complete proof for those functions, g of x, for which this is guaranteed to be not 0 when h is very small. This is a complete proof for those functions. But what I am saying is that the chain rule is more general than that. Even if you have a function which has that property, the chain rule still works. So that part is technical. So you can, you can actually generalize this theorem to conclude that. For example, if I want to give you some clue, for example, consider this function, f of, let me write this g of x, because I want to give an example of a function g of x. Consider it as sine of 1 over x. Okay? And then let me give you a sequence, an, it defined to be 1 over 2 pi n. Momentarily forget about this. Let us consider this sequence. Okay, so this sequence, by making n very large, the numerator is constant, the denominator grows. So this means that this division becomes smaller and smaller. So if this is 0, if I concentrate on this interval, I hope that you understand that there are many of these points inside this interval, no matter how short this interval is. Because by increasing the value of n, these numbers are getting arbitrarily close to 0. So if I make this interval shorter, you can make n bigger, and then you can win the game. Yes, you can make this one inside this interval. If I make it shorter, you can still increase n more, and then you get to my interval. So it doesn't matter. I'm just giving you intuitive ideas, okay? These can be done precisely in mathematics, but what you need at this level is just this intuitive idea. So if I make this even smaller, you can make the n even bigger so that you can make these numbers be inside this. This is one thing that you understand. Hopefully, if there is any question, please interrupt me. Okay, now if I ask you, what is g of an? What is g of an? This means that I need to write sine of 1 over an. Yes? And then, what is 1 over an? Can you tell me? An is this one. 1 over an is, everyone? Hello? 2 pi n. So it becomes sine 2 pi n. But tell me, n is an integer, is a natural number. When I say the sequence, it means that this number is an integer. But what is the value of sine 2 pi n for any possible choices of n from the set of natural numbers? What is, what? No, which constant? Not a constant. Where is 2 pi n on the unit circle? Yeah, the 2 pi n means an even multiple of pi. So it is actually, if you consider the unit circle, 2 pi n is always here, regardless of the value that you choose for n. And then you know that sine is the y-coordinate of that point. The y-coordinate is 0, so this means that g of an is equal to 0. Okay? So this means that it is possible to make this function equal to 0 at some point in any interval close to 0, even though the function itself is far from being constant. This function, you can draw it using GeoGebra. You see that it oscillates a lot. So this function is not a constant function at all. But for this function, you cannot guarantee that the denominator is not 0. So what I'm saying, but the chain rule is also valid if you take this function g of x here. So what I'm trying to say, I want you to understand, none of them would be in exam. They are much more advanced. But for the people who actually wants to understand more deeper, these things more deeper, this is what we are saying. So when we divide and multiply, this is safe unless, this is not safe unless there is a guarantee that this is not equal to 0. But there are some strange functions that we can artifact, something like this, so that this cannot be the case, but still the chain rule is working for them. So it means that we need to prove something more stronger than this way of proving. But this proof is completely okay if you are ignoring sub abnormalities like that. Yes, that's what I wanted to know. But at least you have a very good clue where this formula is coming from. Again, you see that I have started from the definition of the derivative because I don't have anything at my disposal if I want to prove a general theory. Okay, but it was a little bit convoluted, I agree. Okay, any questions so far? I would say that this is enough for the chain rule, but this understanding how to use the chain rule is 100% needed for every one of you, okay? Now, there is a topic in the book, it's called application of the chain rule, so I want to teach that part today. Okay, so let me, if I want to follow the book, it's on page 85, application of the chain rule. So let me start with a motivating example and try to use our knowledge in chain rule to be able to solve this problem. Okay, so let me write a problem here on the board for you. So air is being pumped into a spherical balloon Now that's more or less the same example in the book with different numbers might be. So a spherical balloon in a way that its radius is increasing at a constant rate of 3 centimeters per second. Determine the rate at which its volume is changing when the radius is 2 centimeters. Okay, so this is a question that I want to talk about today and use this as an excuse to talk about what I want to talk about today. So we are pumping air into a spherical balloon. So it is clear that when I'm pumping air into it, the radius of the balloon is changing over time. Then as the consequence of that, the volume of the balloon is also increasing, yes, by some particular rate, which we don't know yet. We're supposed to determine it. And there is no guarantee that the rate at which the volume is increasing is a constant. Okay, it depends at which instant of time you are looking at the balloon. The rate at which the volume of the balloon is changing might be different at different instants. Yes, there is no guarantee, at least, that should be a constant. So we want to find that. Okay, so if you see, how do you think this is related to the chain rule? So we have a quantity called volume of the spherical balloon, and then if you see the formula sheet, you see that the volume of the balloon is equal to, let me write it a little bit further, it's equal to 4 over 3 pi multiplied by the radius cubed. This is what we know. This formula establishes the dependence of this quantity, which is volume, to this quantity, which is radius. Okay? But at least by reading this problem, the rate of the increasing the radius is 3 centimeters per second. So it seems that another quantity involved in this problem is time, and there is no track of time in this formula. So what does it mean? If you think a little bit deeper, this means this formula gives the dependence of V to a quantity which is called radius in this case. But the radius in this setup depends on another quantity, which is what? Time. So let me just use the natural letter T for time. So can I say that V also depends on time now?
Yes.
Yes. V depends on R. When I change R, when the quantity R is being changed, of course, V is also changed. But the quantity R is also changing over time by reading the problem. So V depends on R depends on T. So if I want to write this as a function, I can write it as a function of R. V depends on R. But R itself depends on T. So it means that if I want to be more strict and write it completely, I would say V depends on R, but R itself depends on T. And then this is equal to 4/3 pi. If you want to show that dependence, usually that dependence is implicit in the formula. But if I write something like this is not wrong. You might say that, okay, I don't see T dependence here explicitly, but yes, you cannot see it explicitly, but you can understand from the problem R depends on time implicitly. So I would say that V depends on R depends on T. Of course, I can talk about the rate at which V changes with R. I can also talk about the rate at which V changes by T over time. Yes? So now, if I want to give a name here, do you remember if you compare this with the formula of the chain rule, fg of x, so that was the composition of V and G, and the variable was X. Now that's also the same story. That's the composition of two functions. One of them is the volume, the other one is the radius. V depends on R depends on T, so it means V indirectly depends on T. Okay, if I ask you, calculate dV/dr. Do you remember we usually didn't use Leibniz notation because we told that this is a little bit more complicated, why we should use that. But now it is very important because I'm dealing with different variables. So I cannot ask you, if I say V prime, it's a little bit ambiguous because I don't know what does V prime mean. Does this mean derivative with respect to R, or does it mean the derivative with respect to T? Because I have two variables involved in this problem. So this is why this notation is no longer useful. It's ambiguous. I will prefer the Leibniz notation. Okay? So can I talk about this quantity? Is it sensible to talk about this quantity? Yes or no? This means the derivative of f, I am interested in the rate at which V is changing when the radius is changing. This doesn't care how radius is changing. It's not my problem. It tells you that I look at R and I adjust myself with the change in the radius. Okay? So this means that I am taking the derivative of this when R is the variable. But do you think by reading this problem, do you think this is the question mark in this problem? Yes or no? It might be a little bit, I don't know, this I always take these things for granted. Might be I am a little bit careless when writing. When I say, in principle, I should say, determine how fast. Let me write it in this way. Let me write it in this way. Determine how fast its volume is changing when the radius is 2. That's a better word here, okay? That was also correct, but might be how fast is better. So now by reading this sentence, do you think they mean this or something else? When you say how fast, you are interested in the rate at which over time. So this is not the question mark in this problem. How fast something is changing means the rate at which that quantity is changing over time. So the question mark is not dV/dr, it is dV/dt. which is wanted. Okay? So now it means that I want to calculate the derivative with respect to time. So be careful about this point. So it means that I start from here. VR of t is equal 4 pi r cubed. But I take the derivative of both sides with respect to time. I use the prime here to make sure that you understand everything. But prime here, I'm just telling it in words. I am saying that I take the derivative of this with respect to time, so it becomes 4/3 pi r to the 3 derivative with respect to time. So I am just telling you that I am using this prime for derivative with respect to t. But for taking the derivative of this, I need the chain rule. Yes? What is the chain rule form of this formula? Do you remember? It becomes the derivative of the outer function, which is v in this case, calculated at r of t, multiplied by the derivative of the inner function, okay, is equal to 4/3 pi is a constant, so I don't care about this. But I told you that this prime means the derivative with respect to time. So can you tell me, how should I take the derivative of this with respect to time? So let me emphasize here. If I ask you the derivative of R3 with respect to R, this is easy. What is the answer?
3r squared.
3r squared. But now if I ask you the same thing, d dt of R3, I am telling you, if I don't say anything about R, you will say 0. But now reading this problem, you understand that R is not a constant. R is changing over time. So you are not allowed to write constant 0. So you would write 3r squared, but you need to multiply by the derivative with respect to time. So this becomes dr dt. So I want you to really understand the difference between these two. I am taking the derivative of r when r is the variable. I just simply write 3r squared. But if my r depends on an internal variable, say t, and I am calculating the derivative of that with respect to time, I do as before, but do you remember in the chain rule, we also have an r prime. Do you remember I told you that if you have u to power 3, if you have x to power 3, the derivative is 3x squared. But if I have u to power 3 prime, where u itself is a function of x, you follow the same rule, but you need to remember to multiply by an extra u prime. By the way, you are also multiplying by an extra x prime here, but x prime is always 1, so this is why you don't see it. But if I have a function of x, there is no guarantee that u prime is 1, so you have to consider it. So you have to write u prime here as well. So that is the same idea. If I ask you the derivative of r cubed with respect to r, it becomes 3r squared, finished. If I just out of the blue ask you to write this, the answer is 0. If I don't give you the idea of what r is or how r depends on time, the answer is 0, because you need to say that, okay, r is my variable, but you are telling me take the derivative of this variable with respect to this variable. I don't see any dependence between these two. I would write 0. But now that I see that this problem relates r to time, you don't say that this is a constant, because it is not. So you take the derivative, but you don't stop there. You have to multiply by this extra u prime, which you learned in chain rule. This extra u prime means the derivative of u, the derivative of r, but the derivative with respect to the quantity that you are taking the derivative, so it becomes dr dt. So these are very important things that you need to be careful about. So then this becomes, according to that rule, it becomes 3r squared r prime of t. Yes? So 3r squared r prime. Okay, so this is one way of thinking, but one way was much simpler. You take the derivative of this, it becomes this, and multiply it by r prime. That's it. I just wanted to talk about these symbols that you know. But if you use the chain rule, you don't need to even care about them. You just write the chain rule. You take the derivative of this, it becomes this, and the chain rule itself reminds you, don't forget to multiply it. So then let me write it here. This becomes 3 and 3 are cancelled, so it becomes 4r squared, r prime of t. And this is the derivative of v with respect to time. This is the equality. Now, someone has forgotten to mute the microphone. Please mute that. Okay. And now we want to solve the problem. This is my question mark. And let us read the question once more. Air is being pumped into a spherical balloon in a way that its radius is increasing at a constant rate of 3 centimeters per second. From this sentence, what you understand? You understand the derivative of the radius with respect to time is constant 3 centimeters per second. When you read this sentence, if you want to write it in mathematical symbol, you write it in that way. Okay, determine how fast its volume is changing. So it means that you are interested in to see how the volume, which depends on r, which depends on time, changes. This is your question mark. There is also an extra piece of information. When the radius is 2 centimeters. So it means that the radius r at time t is given to be 2 centimeters. So this is given, this is given, this is wanted. But you have everything here. So you plug these numbers here, 4 pi. What is r? R is 2. So it becomes 2 to the 2. What is r prime? R prime is 3. So you just multiply them as simple as that. It becomes 4, 12, 48 pi. What you need to not to forget is to write the units here. This is the rate at which the volume is changing over time. Volume is, in this problem, volume is measured in cubic centimeters and time is measured in seconds. So it means that this one is 48 pi cubic centimeters over time. So that is the answer to this problem. Okay, now I want to make it simpler. I want you to understand the idea, especially the difference between these ways of taking derivatives is very important. And now I want to give you an idea how usually we solve these problems in a very simpler way. Okay, you don't need to bother that much. I want to tell it in a way that you can see that this is the connection between, this is called the applications of the chain rule. So at least you understand that this function is a composite function. V depends on R, R depends on T, it means V depends on T. And I am interested in this particular problem, the derivative of V with this inner variable, not this intermediate variable. So that was the whole point, okay? Any questions here? Okay, so let me keep the problem like this. Let me go talk about it in general. So assume that you have a function, you have this function, z equals to f, and f depends on g, g depends on x. And then you want to calculate the derivative of z with respect to this variable inside. Okay? So if I want to write it in this way, let me write it more properly. So z, let me write it in this way. Z is a function of some variable u. U itself is some function of variable x. Z depends on U depends on X. The dependence between Z and U is direct, is explicit. The dependence between U and X is also explicit. But when I look at these two equations simultaneously, I understand somehow that Z also depends on X, because when X changes, U changes. U depends on it. When U changes, Z changes. So it means that when X changes, I should expect that Z is also changing. And then I ask, what is the rate when a quantity is changing over another quantity with respect to another quantity? This is a sensible question to ask. What is the rate at which the quantity Z is changing if the quantity X is changing? That is the meaning of derivative of Z with respect to X. But the point is that according to the chain rule, if I ask you what is Z prime, according to the chain rule, prime means derivative with respect to X. This means f prime of U multiplied by U prime. Okay, so this means that if you want to calculate the derivative of Z with respect to X, calculate the derivative of F, which is the same as Z, with respect to its variable. So dz with respect to U. But don't forget to multiply by the derivative of U with respect to X. Yes? So it's a very nice formula. It's, of course, a formula that is easy to remember because it seems like fractions. Of course, they are not fractions here. But it seems it's easy because in your head you can imagine that these two are canceled. It is a little bit of cheating. But then you will get dz of dx. So that is why Leibniz invention and notation is actually very useful, because it's easy to remember. You would say that the derivative of z with respect to x is equal to the derivative of z with respect to the intermediate variable, whatever it is, u, then multiplied by the derivative of that intermediate variable with respect to x. So let me draw a diagram for you. So you need to remember this diagram. So dz, so let me write it in this way. Z depends on u. This means depends, for example, and u depends on x. My goal is to calculate the rate at which this variable is changing with respect to that. So it means that I am interested in calculating the derivative of z when x is changing. Okay, you can do it in two steps. You can calculate the derivative of z with respect to this intermediate variable, and then multiply it by the derivative of the intermediate variable with respect to the last variable. So this is another nice form of writing the chain rule, which is useful in these kinds of problems. Okay, so let me solve this problem now using this idea much simpler. So what I say, I would write that V is 4 over 3 pi R3. If I want to draw a diagram like this for this problem, I would say V depends directly on R. By reading this question, I understand that R itself depends on time. And when I read the last sentence in the problem, determine how fast the volume is changing, it means that the question mark is how fast volume is changing. It means that I am interested in the rate at which volume is changing over time. This is my question mark. When the radius is 2 centimeters, so the radius is given to be 2 centimeters. This is my question mark. Then I need to remind this diagram. You see, dv is not wanted with respect to t. It is wanted, it is not wanted with respect to r. It is wanted with respect to t. So my goal is to differentiate v with respect to the changes in time. So this means that I need to follow this diagram. I think everybody knows how to do. I want to calculate this, but I go through this intermediate step. I would write dv with respect to r multiplied by dr with respect to time. So that is exactly the same diagram that I am writing it appropriate for this problem. My quantities are v and r. Instead of having z, u, and x, I have v, r, and t. Doesn't matter. I'm just copying and pasting that formula for these names. Okay? This is the question mark. This I can calculate. When you want to calculate this, just think that r is x and you are taking the derivative of x cubed. How do you do that? You write 3x squared, as simple as that. But here the name is not x, it is r. So this becomes 4 over 3 pi. And then I have 3r squared. Don't get confused. But then remember that you have a dr dt. You don't need to remember, because if you write the formula in front of your eyes, you immediately see that you have to write dr dt at the end. So this is your question mark. Let me simplify this. So the question mark becomes 4 pi r squared dr dt. Now I want to answer this question mark. Okay? What do I have? I have r. I also have dr dt by reading the first sentence. The radius is increasing at a constant rate of 3 centimeters per second. Centimeters is the unit of length, and seconds is the unit of time. So it is exactly the appropriate unit of this quantity. R is being measured in centimeters, time is being measured in seconds. So everything is ready. You see the solution of the problem. I made it a little bit complicated because I want you to understand the connections. But if this is given in the problem, this you read from the formula sheet, you need to analyze it in this simple way and write the appropriate formula. Just take a very simple derivative. This is just x to the 3 derivative, as simple as that. And then you need to plug the numbers in. So this becomes 4 pi. Instead of r, I use 2 here, 2 to the 2. Multiply dr dt is given in the problem itself. It is 3 centimeters per second. So this becomes 3. And then if you calculate these things, it becomes exactly 48 pi. And then you shouldn't forget writing the units. It's crucial here. And then that's easy. This is the derivative of volume with respect to time. How volume is measured in this problem? Because you see that the length is measured in centimeters, so it is clear that the volume is measured in cubic centimeters, and the time is measured in seconds. So the question mark is this one. This is the answer that you need to provide. So the solution of the problem is from here to here. Okay? This is not mandatory. This is for your information. You even don't need to write that. So the solution starts from here and goes up to here, as simple as that. These problems could be complicated, and they are actually very practical, but we don't have enough knowledge at the moment to solve these kinds of problems. Little by little that we learn about the product rule, we can solve a little bit more interesting problems regarding these applications of this type. Okay, so is there any questions that you want to ask? No? Okay, so I will stop the lesson here. Next time, because there's no time, I might be overtired a little bit. So next time, I'm supposed to go to teach you the derivative of sine and cosine as the streamlined schedule. Now you can see, but because the next lesson is a little bit longer, so I can spend a little bit of that to give you more examples of this, and then we go to the next lesson, which is also a very important lesson. Okay, if you don't have any questions regarding the lesson itself, I can end the stream and then we can go to Zoom. If you have some other things to say, I will be listening to you. But now, right now, if you have any questions, let me know right now about the lesson. So this lesson is on page 85 and 86, and there are a set of problems on page 86 and 87 of the Matematik for Origo book. Yes, I will write this on a Schoolsoft, of course. I recommend you to work on the problems before the next session. Okay, any questions regarding the lesson? No? Okay, so bye-bye. You go back to Zoom, I will be there, okay? Yes, Alex, do you have questions?
I said I don't think anyone has questions.
Okay, we go back to Zoom. I will end this live stream. Bye-bye.